Okay, binomial coefficients. So definition is very simple. So binomial coefficient n choose k is a number of subsets of size k of a set of size n. Okay, for instance, 4 choose 2, as people call it, is the number of 2-element subsets inside a set of 4 elements, and you can pick 1, 2, and maybe 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, which is 6. Okay, so of course there exists an explicit formula for it, and I guess maybe all of you have seen it. So it is n factorial over k factorial times n minus k factorial. So why is that the case? So if you want to prove a combinatorial equality like that, you need to know some basic principles. So what are basic principles? I mean, one of them is that if you have a cardinality of a product of two sets, that's just product of cardinalities. And you can think of it as kind of very close to definition of what a multiplication is. I'm not going into basics how to prove such things, because then we need to talk about axioms and so on. I don't want to do that. That's something I assume you understand. And also, if you have two sets sitting somewhere, then cardinality of a union is cardinality, sum of cardinalities minus intersection. So that's just because when you count the union and you just add them, you count the intersection twice. So using these two principles, it's really easy, and using some bijections to prove something like that. So why? Because imagine, yeah, let's see how to prove it. Well, for instance, you can prove it like that. So suppose you have a set 1 to n and a set 1 to n. So definitely, suppose you want to look at all permutations. So these are bijections from a set to itself. And then let's split our set into parts, size k, size n minus k. And if you want to find a bijection from the set to itself, you can first decide where the first k elements go, and then decide where the second n minus k elements go. So for this, you need to do the following thing. So you need to determine here a subset of size k, which is the image of the map f of 1 up to k. And this has exactly n choose k options, because you just need to pick any subset of size k, and then you know that these k elements go here, the rest elements go to the remaining part of the set, and then you need to choose a bijection between this k and elements in this subset, and there are k factorial such bijections, and bijection from n minus k to the complement, and there are n minus k factorial such bijections. So from here you can see that n choose k times k factorial times n minus k factorial equals to n factorial. That's the proof. I mean, also you can argue in some other way. For instance, you can just, let's try to count all subsets of size k. For this, let's find a bijection of our set with 1 to n. And now let's just take the first k elements being our set, and then we can see how many times we overcounted things. And actually, every subset will be counted k factorial times n minus k factorial times, because when you reorder elements inside the set and outside, it doesn't change the set. So this kind of basic arguments prove you this inequality, this equality, but later on I will kind of explain maybe a better proof. So so maybe more fundamental than this formula is a recurrence relation. So a recurrence relation is as follows. So maybe this is called recurrence formula. So n choose k equals to n minus 1 choose k plus n minus 1 choose k minus 1. So I assume that k is less or equal than n, and here I assume that if k is actually bigger than n, then I just put it equal to 0. So how to prove that? So here let me maybe actually write down a more careful proof, because it's a prototypical example of a beautiful statement about the stuff. So okay, so proof 1, of course one can just get it from explicit formula. Explicit formula. So I mean, just if you just look at that, you have n factorial or k factorial n minus k factorial equals 2, or does not, n minus 1 factorial k factorial n minus k minus 1 factorial plus n minus 1 factorial over k minus 1 factorial n minus k factorial. And when you divide by n minus 1 factorial and multiply on this stuff, you will get the equality. It's equivalent n equals to k plus n minus k, which is true. So there is a really simple, direct, explicit formula proof. But of course that's kind of a bit boring, and also maybe if you don't like my proof of this formula, you want to prove it by induction using recurrence formula. So let's give independent proof. So both of these things, so each 3 terms correspond to something. So let me denote a set from 1 to n by n. That's useful notation. So proof 2 is as follows. So so let's see. So n choose k. So we have on one hand we have a set, all subsets of n of size k. And on the other hand, we have all subsets of n minus 1 of size k and all subsets of n minus 1 of size k minus 1. And the statement is that there is a bijection which identifies all these subsets with either this one or this one. So kind of union of these two sets, if you think of them as not intersecting, is in bijection with this set. So let's do it very explicitly. So for that, consider a subset here, A. So A is inside n. And then there are 2 cases. So element n can be there or not. So this thing is a union of 2 sets. So subsets of size k such that A contains n or A does not contain n. And of course that's completely obvious, because every subset either contains n or does not. I chose this number n randomly, so I can pick any element here that works. So these 2 guys don't intersect. So our set we are looking at, whose cardinality, so this guy has cardinality, so cardinality equals n choose k. So it is actually a union of 2 sets which don't intersect, and then let's look at their cardinality. So if A does not contain n, that clearly such things are in bijection with a subset of n minus 1 of size k, just because I mean a subset there is a subset of the first n minus 1 element set. So this is why there is a bijection. And if A contains n, then you can take this A and just look at A without n, and this gives you a subset of n minus 1 of size k minus 1, because we took away 1 element. And that's also a bijection. And so basically what we have done, we have constructed a bijection between a set of size n choose k with union of 2 non-intersecting sets, and cardinality of this one is equal to n minus 1 choose k, and cardinality of this one is equal to n minus 1 choose k minus 1. And since we know that for two non-intersecting sets, cardinality of their union is sum of cardinalities, we got the statement. So that's the proof, and this is a prototypical proof. So almost all formulas in combinatorics, especially for such simple things as binomial coefficients, can be proven in this or that way using explicit bijections. And sometimes coming up with them can be pretty non-trivial task, because you need to come up with something and it doesn't follow from the formula where this equality comes from, sort of combinatorially. But you should think of this equality as a numerical manifestation of a general principle that if you are counting subsets of size k, they either contain each element or they don't. So this is where this formula comes in. If you are not sure how to kind of write down this proof carefully, I recommend you to do it very slowly and give one of your instructors it to check, the proofs of similar statements from the homework. If you are not sure how to use induction, you can practice here proving, for instance, from this recurrence formula, this formula by induction or something like that, and again prove things in our homework by induction. But if you feel that this is all simple, then you are in good shape and you can actually start giving proofs by sort of explicit bijections of very interesting identities. And believe me, this becomes very hard soon enough. So like a few first are simple, but it is very easy to come up with identity which is beautiful, which is amazing, and nobody knows a good combinatorial proof. So we will do later on more complicated identities like that, and we will see more complicated arguments with explicit bijections. But what I'm again trying to emphasize is that if you just prove everything using explicit formulas, you kind of miss the most beautiful part. Okay, so if you have any questions about this argument, again, you can ask them during office hours, which will be on Thursday, or during classes. This is the main property of binomial coefficients. And by the way, it's kind of important to know that n choose 0 is equal to 1, and choose n is equal to 1. There is only one subset of size n and one subset of size 0, which is empty set. Okay, so let's now see how people actually draw this binomial coefficients, and this is what's called Pascal triangle. Okay, so Pascal's triangle. So that's not only pretty, but it is really useful to think about binomial coefficients. So the idea is very simple. So we just draw a triangle, and let me just draw a piece of it. So we start with 0, 0, which is kind of 1. Then we write 1, 0, 1, 1 underneath. 2, 0, 2, 1, 2, 2. 3, 0, 3, 1, 3, 2, 3, 3, and so on. So we just write for fixed n, we just write all these elements one after another, and every next row is on one element longer than the previous one. And of course, the main idea is that using a recurrence relation, we can actually draw it very fast. Because, let's start. So we know that we have 1 here, and you should think that everything kind of to the left and right is equal to 0, and every element of Pascal's triangle is a sum. So if you have A and B on top left and top right, you write A plus B underneath. And so we start with 1, 1, 1, 1, 1. So there is only a 0 element size set is just 1 and one set of size n. So it will have ones everywhere. So then you think that zeros are just outside everywhere. And then you just sum up two terms on top. So you have 2, 3, 3, because you sum up these two guys. 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and so on. So this is a picture, and this is called Pascal triangle. That's very beautiful. So it has tons of interesting mathematics related to it, and we will see some. But if you are feeling that everything is like totally obvious here, you can immediately puzzle yourself, for instance, with a question, which of these numbers are even, which are odd, and which are divisible on which power of 2, or something like that. That immediately leads to interesting mathematics, like very fast. That's something. We will talk about this number theory related to Pascal triangle later on. Before we do that, let's prove a few more combinatorial identities. So one of the most famous is that if you sum up all elements in each row, we'll get power of 2s. 1, 2, 4, 8, and so on. So formally speaking, sum and choose k from k equal to 0 to n equals to 2 power n. So how to prove this one? So again, I want to use this as an excuse to actually show you some ideas. So proof number 1, I mean, okay, so the simplest proof is probably induction, but even that I want to do slightly in a fun way. So of course you can prove it by just you just prove it by induction using the previous formula, because you just say that the sum and choose k is equal to sum and choose k minus 1 from 0 to n plus sum n minus 1 k minus 1 from 0 to n. And then you should be slightly careful, because the summation from 0 to n doesn't exactly make sense. For instance, so if you sum up from 0 here, sort of start with minus 1, but we think of it as 0. And here when k equals to n, no, that's fine. Yeah, so you should be slightly careful here, but eventually you get, of course, 2 power n minus 1 plus 2 power n minus 1, which is 2 power n by induction. But another way to just think about it is not to use any identities, because you know we have here some indices of summation. You should be careful, you should check everything. You can look at the picture instead. So we just know that every element here is a sum of elements to the left and to the right. So for instance, like 1 is 1 plus 0, 4 is 1 plus 3, 6 is 3 plus 3, 4 is 3 plus 1, 1 is 1 plus 0. And so if you use it, then you know that sum of these elements is of course twice sum of the previous column, because we will sort of sum up 0, 1, 3, 3 with 1, 3, 3, 0, 1, 3, 3, 1 with 1, 3, 3, 3, 1, 0. So we don't sum up exactly the same thing, but every time we add kind of 0 on one side or 0 on another side, and they don't change anything. So that's why it is just twice the previous power. So that's the proof. But of course, that does not explain where 2 power n comes from, and better proof is using explicit bijection. And this is really simple, because let's consider a set of all subsets of n. So all subsets of all sizes. So if you look at this set of all subsets of all sizes, of course it has sort of cardinality equal to 0, cardinality equal to 1, and so on, up to cardinality equal to n. And for each of them you have n choose 0, n choose 1, and so on, n choose n subsets. So if you look at this set of all subsets of this set from 1 to n, usually people will denote it by 2 power n, and this is pure notational, doesn't mean anything. So this is of course its cardinality is equal to sum and choose k. So at least we found a beautiful combinatorial interpretation of the left hand side. So the question is why the number of all subsets equals 2 power n. And the answer is, again, let's construct an explicit bijection. So so claim, which is very important, is that there exists a bijection between subsets of n, all of them, and sequences sequences x 1 up to xn, where xi equal to 0 or 1. So you should think of it as sort of computer science bits sequences. So of course this then of course this number of subsets is just equal to cardinality of 0, 1 power n, which is 2 power n. So this implies the result. Why this is the case and why it is important? So the proof is very simple. So let's just code every subset. So suppose you have some subset A inside n, and then we just write a sequence. So let's send it to a sequence x1 up to xn, where xi equal to 0 if I is not inside A, and xi equals to 1 when I is inside A. So in this way, our sequence just codes which elements of the set are there, which are not. For instance, if you have a subset 1, 3 inside 1 up to 4, then we will code it by sequence 1, 0, 1, 0, because 1 is inside, 3 is inside, 2 and 4 are not. So that's what our sequence looks like. Okay, so this is interesting, and this actually, the story goes actually much further, and this correspondence, this bijection, has a deeper meaning. So maybe I want to say a few words about it, because we will probably see such ideas later on. So the main idea is that one can view such sequences as vectors. So remember from high school probably that vectors are this sort of arrows on the plane, and you can sum them and multiply on scalars and scalar multiply and so on and so forth. And so the idea is that using this bijection, one can think of subsets as kind of vectors, except that coordinates there are only 0 or 1. So, okay, let me talk about that for a few minutes. Okay, so if you have taken already linear algebra course, everything here will be kind of obvious to you. If you have not taken, I will definitely confuse you. But this is always what learning mathematics is about. You are kind of going on a short road between obvious and you don't understand a bit. And obvious usually means you're just used to not understanding that. And we are going to do exactly this right now. So if you will be lost, that's totally fine. I'm not going to use it soon at all. But still. So again, we have a set from 1 to n, which I denoted by n. So I want, and I have two symbols, 0 and 1. So this 0 and 1 has nothing to do with this 1 up to n. So I want to introduce some operations with them. So firstly, for this set, I will introduce notation F2. And if you know what fields are, this is exactly a field with 2 elements. But this is just a set for now. And then I want to introduce operations, addition and multiplication. So, operations are just, maps from F2 times F2 to F2. So they take 2 elements and do something with them. And I just need to say what happens when you add 0, 1 with 0, 1, and when you multiply 0, 1 with 0, 1. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 0, 1 plus 1 is 0, 0 times 0 is 0, 0 times 1 is 0, 0 times 1 is 0, 1 times 1 is 1. So where this came from? So there are 2 interpretations, which you have probably seen, or at least one of them. So one of them is you can think of 0 as kind of even numbers, for instance, thinking about integers, and 1 as odd. And then you know these rules, you know, odd plus odd is even plus odd is odd, even plus even is even. So this reconstructs this part. And you know that even times odd is even times even is even, odd times odd is odd. And this reconstructs this part. So another interpretation is, and then addition is just, you know, you add numbers and think whether sum is even or odd. There is another way. One can think of 0 as false, and for 1 as true. And then addition will be an operation called OR. And multiplication is an operation called AND. So whether statement and statement is true if you know that two statements are true. So wait a second, is it correct? Nope, that's not OR, that's XOR, sorry. So XOR means that two statements are true or false simultaneously. No, sorry, XOR. XOR is true if one is true and another is false. Sorry, so it's like exclusive OR. So OR but not AND. And this is exactly that. And if you introduce this notation, then a lot of usual properties like A plus B plus C equals A plus B plus C and so on are satisfied. So lots and lots of them. So all usual properties of addition, multiplication, division actually, and so on. I'm not going to talk about this in that much detail because we will see later on some other fields and we will probably discuss it a little bit more in general, but so far I just introduced some operation arithmetic with this zeros and ones. And then, let me think of the space f2 power n. So these guys I will call vectors. And these are just sequences, x1 to the xn, just sequences of elements in f2. So I call them vectors and I will denote it like v1 and so on. And the reason is because I can actually introduce operations with them. So I can consider v1, which is x1, xn, and w1, which is y1, yn. And then I can do what usually you do with vectors. So firstly, you can add them, or say subtract. And of course, you are probably used to this vectors of lengths maybe 3 or 2, but the same works for n, and maybe in analysis you have already seen that. So you can add them, you can similarly subtract, but you can notice that sort of here minus and plus is the same thing, just because, I mean, -1 is something which you need to add 1, 2 to get 0, so it's also 1. That's just the same thing. And also, I mean, you can multiply it on element of f2, so 0 times v is of course just 0, and 1 times v is of course just v. Nothing else to multiply on. And finally, you can even introduce scalar product. So v1 times w1, and you just use the standard formula sum xi yi, which you probably know from high school. 0 to n. Okay, so and this structure, this vector space, has tons of properties. It's really important and one can apply fancy mathematics to it. Maybe we will do a little bit of that later on, exactly for this combinatorial kind of vector space. But I'm not going to do it right now. I just want to show how this all algebra interplays with combinatorics. So firstly, I remind you that there exists a bijection between subsets A inside N and vectors V inside f2 power n. So I need some name for this bijection. Let me call it vector of A. Okay. And then I can try to see whether this bijection has any nice properties. I mean, other than this is a bijection. So for instance, I know that empty set will go to just 0, 0, 0, 0 vector, which is cool. Origin. And if you apply this bijection to A as a subset of, to the whole thing, to N, you will probably end up with vector 1, 1, 1, 1, because just all elements are there. But here we have a beautiful operation, sum. So what is that? And the answer is, so if you have two sets, A and B, are subsets, then just define their symmetric difference to be A union with B minus the intersection. So this is called symmetric difference. And geometrically, you just draw two sets and you take all elements except those which are in the intersection. So everything except the intersection. And then it's really easy to see that V of A, this symmetric difference with B, is V of A plus V of B. And the reason is very simple, because when you add two coordinates, x plus y, as we saw, it equals to 1 if one of them was 1 and another was 0, meaning element was here or here. And it equals to 0 if it was in neither of the sets or in both. So that's why. That's very simple. Also, one can ask what is a scalar product. And for instance, one can ask what is V of A scalar product V of B. And this is actually just cardinality of the intersection modulo 2, which I leave as an exercise, and maybe later on we will see how one can use it to prove something powerful. So this was just a digression. Let me say that for those of you who have taken some linear algebra, this vector space is a vector space. It has dimension n, and you can use it and use a space and use this scalar product and use this sum vectors and bases and so on to prove some interesting problems in combinatorics, and we might talk about it later on. So I just wanted to elaborate on the fact that this bijection between sets and sequences not only proves how many sets are there, but also has remarkable properties. Okay, so let's move on then.